Right, good evening, everybody. Can you hear me okay? Okay, I can never tell whether I'm being amplified or not, so apologies if I shout sometimes. Welcome to Jodrell Bank again. We've had some bad weather in other places, but Jodrell Bank's lovely again, as always. Thanks for coming along. So what I want to do is I want to tell you a little bit about what our telescopes are doing, basically. So rather than a talk particularly about the science that the telescopes have done, it's more about how the telescopes do the science and what's sort of behind the scenes, if you like. So a bit different than the sort of thing we would normally talk about. So we're all sort of used to seeing views like this, I guess, if we go to a reasonably dark sky site. I don't know whether, can we switch these lights off that are at the front over there, or, sorry, they're sort of shining on the screen, I think, so maybe the ones there are as well. There's some over here as well, isn't there? Oh, sorry, am I making... Oh, I feel really bad now. I should have thought of that before. Sorry, thank you, thanks. Sorry about that. So this is the sort of view we get at a dark sky site and a dark room site. Which is basically stars. So what we see when we see the stars at night, what we're seeing is the hot surfaces of glowing balls of gas. So typically, like the sun, for example, the surface of the sun is about 6,000 degrees, and that causes it to glow in visible light. And that's pretty much true of all the stars. They're all different temperatures, but we're seeing them. It's visible light that we see with our eyes. If you go to a very dark sky site, sorry, I'm just showing you some of my holiday photographs here. The last one was from a lovely place at the side of Loch Fyne in Scotland, and this one is from a lovely place which is the South African Astronomical Observatory, sort of inland from Cape Town. But if you go to the southern hemisphere and you go to a dark sky site like this, then you get a glorious view of the Milky Way galaxy. So this is the centre of our own galaxy. Has anybody seen the Milky Way themselves? Who's seen the Milky Way? Few people. So, you know, much less, probably only about 10% of people stuck their hands up, I think. So you need to get somewhere dark. You can see it from this country. You don't have to go to South Africa. You'll be pleased to hear. But if you get somewhere away from city lights, well away from city lights, and you let your eyes get used to the dark on a clear night, you see the Milky Way sort of arching overhead. From the southern hemisphere, you get to see the middle of the Milky Way. So you get to see these sort of these dust clouds, these dark clouds that basically are clouds of dust between the stars, and they block our view of the more distant stars, and so they appear as these sort of dark patterns in the night sky against the background of the many millions and even billions of stars in our own galaxy. If you take a sort of a photograph of the whole sky around us, and so this is done by taking photographs like the last one, which I just took with an SLR camera and a sort of fairly normal camera, 30-second exposure of the night sky. If you do that from various locations around the planet, and at various times of year, you can piece together all the pictures and you can make a map of the sort of whole of the sky around us. So the way to think about this picture, the bit of the Milky Way that you just saw in my photograph was somewhere in the middle here, but just a section. If you imagine that this were a map of the Earth in an atlas, when you look at an atlas and you lay open the atlas and you look at a map of the whole of the Earth, you generally would see the sort of North America and South America is typically down here, and you know the UK is somewhere up there in the middle for culturally historical reasons, and Africa's down here, and Asia's up here, and Australasia's down the bottom right hand corner. But that map of the Earth, as I'm sure you all know, is actually just the surface of a globe, the surface of a sphere that's been unpeeled and laid flat, right? There's nobody thinks the Earth is actually flat here. We usually like to check, and Lexi's ready. She was on hand then to drag you out if you did. So the Earth is round, and basically, if you imagine looking up at the sky around you, it's a big sphere around us as we look out. So you can make a picture of the whole sky all the way around us, from below our feet to above our heads and all the way around, and you can lay it flat, and that's what you see here. So the Milky Way, our galaxy, runs across the middle of that picture, and really to get the full experience, you have to sort of get hold of the right-hand edge of this picture and start unpeeling it, and go get hold of the left-hand edge and start unpeeling that, and then you have to take it and you have to wrap it around your head and join it together at the back. So this whole thing is all the way around us and covers the whole sky. But this is all stuff that we see with our eyes, and of course that's not everything that there is. Our eyes only see a limited bit of the universe, effectively, because we only see visible light. And we have a lovely photograph here by our computer manager, Anthony Holloway. Took this lovely photograph, snapped a picture of a rainbow over one of our telescopes, and the rainbow of visible light is what your eyes can see, but of course beyond the rainbow you have beyond the red, you have infrared and then microwaves and radio waves, and beyond the violet you have ultraviolet, X-rays and gamma rays that make up the full electromagnetic spectrum. And as astronomers these days, we would want to look at all these different wavelengths of light, we call them, and each one will usually give us a different bit of information about the things we're looking at. So it's almost like a little jigsaw puzzle that, we have a visible light bit of the jigsaw and a radio bit of the jigsaw and an X-ray bit of the jigsaw, and we stick those bits together and we then get a complete picture of the objects that we're looking at. So Jodrell, of course, is famous for its view of the radio sky using radio telescopes. So here's the visible sky again. If we now switch to what a radio telescope sees, then it looks like this. And I should explain what the colours are in this case. You sort of understand what colours are, I suppose. If you're using your eyes, you probably have a reasonable idea of what red and blue and green are, although knowing what other people see is actually quite hard to work out, and my perception of blue and green is different than other people I know, and so there's a bit of confusion. But anyway, generally you know what colour means with visible light. With a radio image like this, all we've done is we've used the radio brightness, so the strength of the radio signal is mapped onto the colour. So where it's black in this picture, that's a weak radio signal, and then it goes up through various shades of this lovely pink colour and ends up with white, where the brightest radio waves are. So it's only representing the strength of the radio signal coming from the sky. But what you can see is that there's a sort of horizontal line. So there's your Milky Way, our galaxy, and in the radio image there's still something running across the middle. It looks a lot thinner actually, it looks a lot thinner in this dimension compared to the visible light picture. The other thing that's different is if you look at them right in the middle of the picture, right in the middle of the Milky Way here in visible light, you see some glow, some bright glow. This is coming from lots of stars in the bulge of our Milky Way. But these dust clouds between the stars block our view of the very centre of our Milky Way galaxy. Whereas if you go to the radio waves travel straight through those dust clouds, and we see right down into the heart of the Milky Way. And this is a supermassive black hole weighing about 4 million times as much as our sun, sitting in the middle of the Milky Way, which we weren't aware of these sorts of black holes till we started observing the universe with radio telescopes. As just as a matter of interest, this thing here is a distant galaxy, way off in the distance beyond our own Milky Way galaxy, and there's a supermassive black hole at the middle, and jets of material are shooting out in opposite directions. It's called Centaurus A. It's in the Centaurus constellation, so it's the brightest radio source, so it's called Centaurus A in that constellation. This is huge on the sky. This is the whole sky all the way around us. So it's a great pity we can't see with like little radio dish eyes and look up at the night sky and see this spectacular thing sitting in the night sky. So you see different stuff. You see through dust clouds, and in fact, in this case, the radio waves are not coming from the stars. They're not coming from the hot surfaces of stars. They're coming from, in this particular case, electrons spiraling around the magnetic field of our galaxy. So the stuff between the stars is what's producing the radio emission in this picture. And I should just say, the reason the Milky Way is a sort of line, a band on these pictures, is because it's a disk. It's like sort of two dinner plates stuck face to face. It's a thin disk, and our sun is about 2/3 of the way out from the middle of that disk within the disk. And so if you have to imagine things in your head a lot in astronomy, because we can't easily go there and look at things. So if you imagine being 2/3 out of the way from the middle of a disk, and you're inside the disk, if you look in directions that are along the plane of the disk, you'll see lots of stars off into the distance. But if you look perpendicular to the disk, either up or down, then you see far fewer stars because it's a thin disk. And so this direction across the middle is looking in the plane of our Milky Way, and when we look up or down out of it, we see far less stuff, and often it's easier to see farther out into the universe by looking in those directions. So here I'm just zooming into this bit here. So it's the bit over the left-hand side of this picture, and I'm just sort of identifying a few well-known constellations. So Cygnus and Cassiopeia. So the sort of Cygnus, the swan, and Cassiopeia was the queen whose daughter was Andromeda, if you know that mythology. But these are the stars of Cygnus and the stars of Cassiopeia, sort of identified with the lines. The W of Cassiopeia identified there. If you look at the same bit of sky in that radio picture, and I've superimposed again the lines of Cassiopeia and Cygnus, you'll see these two very bright radio sources of radio waves, called Cygnus A and Cassiopeia A. They're some of as you can see, they're some of the brightest sources of radio waves in the sky. But when you look at the position of, say, Cygnus A, really, really bright compared to almost everything else in the whole of the radio sky, and you compare it to the bit of sky up on the visible light picture, there's nothing there. So it's completely remarkable. You know, we knew this sky and sort of looked at it with our eyes for thousands of years, but as soon as we started looking at the sky with radio telescopes, new things popped out that we did not pay any attention to before. If you zoom in on that bit of sky where Cygnus A is with a large optical telescope, what you see this is zoomed right in. These things are stars. These little bright blobs are stars in our Milky Way. But between the stars, you're just about to start to see this little fuzzy blob. So this little fuzzy blob is another galaxy, way off beyond our own galaxy. So we're sort of looking through our galaxy, and way off beyond it, there's this little faint galaxy there that you can see. But if you zoom in on Cygnus A with a radio telescope, this is what you see. And these two pictures side by side at the top are on the same scale on the sky. So they're zoomed in, but they're basically, you know, identical bits of sky. And there's just such a huge difference between them. And again, the colours in the right-hand one are just relating to the brightness of the radio waves. So in this case, I'm not using a nice pink one, I'm using a nice orangey colour table where we go from black through to white, but through these various shades of orange and red. You don't see any of these stars. Don't appear in this picture because stars are actually very faint in the radio sky. They put out most of their energy at wavelengths like the visible, which is why we're aware of the starry night sky. But right in the middle, just where the fuzzy blob is, in the middle, in the visible, you see this little bright spot. That's the supermassive black hole at the middle of that galaxy that you see. That's a galaxy of stars, visible just faintly in the optical. But here, this remarkably bright radio source is a supermassive black hole with thin jets of material shooting out from the region around it in opposite directions, and they're moving at speeds almost the speed of light. Jets of material shooting out, and they crash into the stuff between the galaxies, a bit like sort of firing a hose pipe into a sand pit or something. And so it splashes into the sand, and this is the splash where all the sort of kinetic energy of this jet of material is being converted into random motions of the particles, and that produces the radio waves that we see. So that double source structure on the right hand side was discovered here by by Mrinal Das Gupta and Roger Jennison back in the early 1950s, although this is a much more recent photograph of it now. So I just want to take you back to those sort of early times when the radio astronomy started here. This is an extract from what used to be called the Manchester Guardian, before they upped sticks and went down south. Made a mistake, I'm sure. Should have stayed around here. But this is a little article from Manchester Guardian, November 1948, Radio Astronomy, a New Science in Manchester by Bernard Lovell. And I just quite like because at that time it was new. With its overcast skies and smoke, Manchester could scarcely be regarded as a paradise for astronomers. Yet the university has been bold enough to take a pioneering share in founding a new branch of astronomy. So it's sort of fun. I mean, we don't have as much smoke these days, but we probably still have overcast skies, I'm afraid. Here we are today. Sorry, and I should say, what I meant to say was, the handy thing about overcast skies and radio astronomy is the radio waves go through the clouds. So we can do radio astronomy through the overcast skies of Manchester. So that's why we can get away with doing it here, and we don't have to go to somewhere, we wouldn't want to go somewhere exotic like Hawaii, of course. So, we'd much rather be here in the swamplands of Cheshire. So here we are. This is an overhead view from some proprietary internet-based search engine. So we see Jodrell Bank from above, and we see the telescopes, and we see actually the building we're in is the one up there, just underneath the L and the B of Jodrell Bank, we see the new SKA headquarters building here. Is this big building here? That's our control building here, and the sort of historic original part of the site is at the bottom down there. I mean, here's a sort of slightly better aerial photograph fairly recently. That shows some of the telescopes actually. So it shows the Lovell telescope. It shows the Lovell telescope very obviously here. It shows the Mark II telescope, which is our second largest telescope over here. That just looks so weedy compared to this one. But if we didn't have this one, everyone would be loving this telescope. I feel very sorry for the Mark II telescope. It's great. And then actually there's another couple of telescopes visible in this picture, but only just. One of them clearly needed a jet wash when this was taken. They do get a bit you get a bit mossy basically, growing on the surface, and every now and again we just clean that off. But and there's another one in there that I'll tell you about in a minute. So here's the Lovell telescope. More than 60 years old. 1957 it was completed, but it's still one of the largest telescopes in the world and still able to work at the cutting edge. This is a little time lapse of it I did recently. So it shows you in operation. Right at this minute, the telescope is out of action because we're replacing the back surface, the bit on the left now, the underneath bit, which is a different surface than the one on the right-hand side in this picture. So this surface that you see facing towards you now was put on in 2001, 2002, and that's its third surface. It had an original surface, a new surface built above it in 1970, and then that surface was replaced in 2001. So we've gradually improved the surfaces, but we're having to replace the original surface at the moment because it's gradually decaying. So that's the Lovell telescope. This is the Mark II telescope, which, as I say, is a beautiful telescope in its own right, with this sort of lovely concrete yoke structure at the back there, with concrete built in 1964. Concrete was, everything's built with concrete in 1964, but lots of, new material and very, very popular. So it's a great thing. The world's first telescope to be controlled by a digital computer built by Ferrantes. In Manchester, who are a pioneer in computer development. This is the telescope that's on the side of the control building. So it's the one that I pointed to that I said it needed a bit of a jet wash in that last photo. It's called the 42-foot telescope. The Mark II is called the Mark II because the Lovell telescope outside used to be called, originally it was called the 250-foot telescope, and then they built the Mark II. and then thought, oh, what are we going to call it? Oh, we'll call it the Mark II. Well, we'll rename the 250 foot the Mark I. So they called that the Mark I. It's now the Lovell. This one is named after its diameter as well, 42 feet in diameter, so about 13 metres in diameter. Used to be a missile tracking telescope in Woomera in Australia, and when that came to an end, we shipped it over here and repurposed it for radio astronomy. And the other little telescope that I sort of pointed out where it was and you couldn't really see it is we often called the 7 metre telescope. It's actually a 21 foot telescope. It's exactly half the diameter of the previous one, also came from Woomera. And if anybody's quick at calculating what 21 feet is in metres, you'll find it's 6.4. So we should have rounded that down to the 6 metre telescope, not the 7 metre, before anybody hauls me up on it. It wasn't my decision. So here's a little movie of the 7 metre operating. So the 7 metre is used by our undergraduates typically in the physics department to make observations when they remotely from Manchester and when they visit here as well. As is, you can see the little 42 foot at the bottom moving about, as well as the Lovell telescope there in the background. So you've got in the background you've got a 250 foot diameter. Then just in front of it you've got a 42 foot diameter, and then right in the foreground you've got a 21 foot diameter. So it's a bit like that episode of Father Ted with the cows, and you know, the farther away they are, the smaller they look. Right, I'll just show you a bit of the 7 metre telescope in operation with any luck. Let's see. Okay, so this is a live data stream from the telescope. Just make that big. So it's actually showing you, there's a number of things going on in here, which I'll just explain to you. But basically this graph up the top here is showing you the strength of the radio signal the telescope's picking up, plotted that's on the y-axis, on the vertical axis of that graph, plotted against time over about 10 minutes or so. So the vertical line that keeps moving, that's now, and then every now and again it moves to the right. So the history of what the signal used to be is off to the left, right? And gradually it's writing over the top of what's here. So it sort of shows you what the signal is over the last, you know, several minutes. And you can see it's not doing very much. I actually don't quite know what happened there. It happened while I wasn't looking. But basically what you see is mostly a flat thing because the telescope is actually pointed in a particular direction, and it's actually just tracking. In other words, it's just following that point on the sky. So as the Earth rotates to the east, which is over behind you, then things in the sky appear to move from the east to the west. The sun rises in the east, sets in the west. So if you want to track an object in the sky, your telescopes have to continually move to cancel out the rotation of the Earth. So if you're tracking an object, in general, you'd expect to see that line be flat, because you know, unless you know something happened in that direction in the sky and got very bright, or unless when they get nearer the ground, you start to pick up radio emission from the ground, and the signal will get stronger for that reason. The other thing that's in here is what's called a spectrum. So this is now that's like the total strength of the signal that you're getting, and this is the signal split up across the various radio frequencies within the bit of the spectrum that this telescope is tuned to. So just like if you tune in you tune your radio to a particular frequency to pick up a particular station, you could sort of tune that frequency around and look at different stations at different channels. We've basically got different channels of radio here that we're picking up at the same, all at the same time. And you see the sort of signal changing. It's collecting data all the time, and it's just updating this spectrum all the time here. And you see basically these wiggles are basically a noise, so they're just random noise. They don't mean anything, and they sort of change from typically would change from one instant to the next. It sort of drops off at the edges because you're just looking at this bit of the spectrum. You can't look at everything at the same time, so your receiver's looking at a chunk of spectrum, radio spectrum, a bit like having a filter where you just have a red filter, and you look through a red filter, you only see the red wavelengths. You look through a blue filter, you only see the blue. Here we're looking through this particular filter at a range of radio wavelengths. The radio wavelengths are round about a wavelength of 21 centimetres. So the radio waves are sort of going up and down with a wavelength of 21 centimetres. Now that thing there is sort of randomly going up and down, but you can probably see there's sort of some structure in here that stays the same. This graph here helps us with this because this thing is what's called a waterfall plot, although this is an anti-gravity waterfall plot because the line's going upwards instead of downwards when we programmed this some years ago. So what we see in this is you see the same bit of spectrum across here. So this is the same as this thing in the background in terms of what's happening horizontally, but it's a bit like that thing up there in the sense that where now is the horizontal white line that's gradually working its way up the screen, and then it'll start again at the bottom. The colours are the brightness of this spectrum at all the different places along it. And now you see there was a sort of hump, a sort of peak on the left-hand side there. So I'll go back to that. There's a sort of hump here, yeah, and then there's a sort of hump there. So in this particular colour table that we're using in this thing, we see the hump here is just some sort of broad structure, and I think it's probably just to do with the sensitivity of the filter, the throughput of the filter that we're using. But there's something interesting here actually, because you can't really see it on the original thing, but there's actually two. You now see these very obvious two bright. These are bright peaks. One's a bit broader than the other, running up there, really stable. And this is where your eye is very useful in these waterfall plots. In fact, when you look back at it now, if I'm looking at it on my computer screen, and you might see it, there's actually probably three, because the right-hand one is sort of two sort of merged together almost. Yeah, and you wouldn't see that really there. You couldn't really tell. But because your eye's really good at picking up patterns and connecting the dots effectively, in these sorts of pictures, it's so obvious. It's unbelievable that there's a structure there. That is radiation, radio waves coming from hydrogen atoms in between the stars of the Milky Way. So within the spiral arm structure of our Milky Way galaxies, there's hydrogen gas between the stars, and those hydrogen atoms produce radio waves at a wavelength of about 21 centimetres. And that's what this bright band is running through here, just in the direction the telescope happens to be pointing, somewhere up to the north at the moment. And actually the reason that there's the different lines are actually different spiral arms that the telescope's looking through in that direction. And they appear at different places in this. They appear, one's here and the other one's separated to the side and maybe split into two. You're looking in one direction and there's a nearby spiral arm and then a couple of more distant spiral arms. Where they appear in this is determined by the Doppler shift of the radiation. So it all sets off at the same frequency, but because you're moving at a different speed, the telescope is moving at a different speed relative to these spiral arms. They move, they're either red shifted or blue shifted in the spectrum, so they either move to the left or the right in here, and you see the structure. So there's a huge amount of information in just these sorts of pictures that we can build a model of the Milky Way galaxy, and we can compare, we can make measurements of the positions of these lines, and we can then construct our picture of what's going on. I might just set running, and it takes. I can actually scan the telescope across one of those bright objects that we saw in that map. I saw two objects. One was in Cassiopeia and one was in Cygnus. So if I just scan across, Cassiopeia here, and I say start scan, then with any luck, the telescope information system up here will tell me that it'll start, basically drive the telescope across the sky, cutting through the middle of one of these bright radio sources. It's same weighting at the moment, but hopefully if the system's still running, it was last time I tried it an hour or so ago, it should pick that up in a minute and start an observation. I can sort of see, well, actually I can see where it's actually pointing, and where it's demanding it point is different, so it's doing something. So we'll come back to it because we don't want to wait, and it takes 5 minutes or so to do that. So we don't want to do that. If I can get back, let's get back to my presentation. Okay, so now there's a problem with radio astronomy, and the problem is to do with something called diffraction, which I don't know whether you've ever seen, done an experiment with water waves sort of going through used to do it at school. You have a sort of water waves in a tank, and you have a little aperture, and you set these water waves going, and they move in the tank, and they go through a hole in the aperture. And if they go through, if these water waves come in like this and they go through the hole in the aperture, they sort of spread out on the other side. I should have put my picture. I should have put one of my other holiday snaps in. Damn, forgot. If you go to Whitby has these lovely jetties, doesn't it, that sort of come together. If you stand on the hill above the harbour and you look down, you can see the sea waves coming in parallel, and then when they go through this aperture, they sort of do this. Anyway, I do have a picture of it. That's not the only things I take pictures of when I'm on holiday, but I like to spot these things. So what happens is that it's intuitively obvious that if you widen that aperture up, you have less effect on the waves coming through. The narrower you make the aperture, the more of an effect this sort of opening out thing becomes. You know, once this thing comes down to being very narrow, it's almost as if the waves are all setting off from the same point, and so you get this very sort of spherical wavefront coming out. That's called diffraction. What it means is that if you look at something that actually should be just a dot, it should be just a point on the sky, instead of seeing a point, what you see is this. You see a blurry blob in the middle, and you see these rings around it. That's the typical, what's called the diffraction pattern of a point source. So that effect leads any optical system, could be your eye, could be the pupil of your eye, is basically like this aperture. So your pupil's maybe 5 millimeters across or something when it's opened up a bit. A radio telescope out there like that one is 76 meters across. But both of them collect the waves coming from light waves or radio waves, and they're basically like this aperture. So the smaller the aperture, the more of this diffraction effect you get. So in fact, you get a blurry view. If you've got a small aperture, you get a blurry view because of this. You get more diffraction. The larger aperture you have, the sharper the view you get. And if you're interested in equations, this is the sort of a famous equation called for resolving power, where basically the angles you can see, the sort of variation in structure you can see, is given by the wavelength divided by the diameter. So it's the wavelength of light you're looking at divided by the diameter of your aperture. So if you want this to be able to see tiny details, you want this angle to be small, and so in this equation you either want the wavelength to be small or you want the diameter to be big, and that would give you a small number in here, and that would effectively means a sharp view. The problem I referred to for radio astronomy is that radio waves, I mentioned these waves from that 7-meter telescope are 21 centimeters in length. That's something like 100,000 times bigger than the wavelength of a visible light wave. So in this equation, the lambda for radio waves is 100,000 times bigger than visible light. So if you want to be able to see with a radio telescope the same detail as you would see with a visible light instrument, whether it be a telescope or your eye or whatever, you need to cancel out that 100,000 times bigger with 100,000 times bigger diameter. And that'll cancel it out and you get the same sharpness of view, which is a bit of a challenge, right? Because if you think about your say your eye pupil is 5 millimeters in diameter, what's 5 millimeters times 100,000 times 100,000? The 1,000 will get you to meters, and then the 100 will be, so it'll be 500 meters. So you'd need a radio telescope 500 meters across to get the same sharpness as view as just your eye gets looking up at the sky. So a radio telescope like the Lovell telescope has a much blurrier view than your eye gets. Okay, so that's a problem. Let me just have a look at that thing I was just doing, see if it's finished. Or even see if it started. That'd be the challenge. Oh, it's not. Oh, that's weird. Where's it gone? I've lost my window. Oh, where it appeared while I was looking for it. Great, good timing. So this is actually the result of scanning across that bright radio source that we saw in the sky in Cassiopeia. So you see the telescope's moving across the sky, there's the radio signal, and as you go across the object, it rises and then it falls again on the other side. This is actually labelled in degrees on the sky, and the sort of width of this, the width down to here is about 4 degrees, about 2 degrees across about here. The full moon on the sky is about half a degree across. So the full moon would be about this diameter on this thing. So it's seeing a blob much bigger than the size of the full moon. In fact, the actual thing, that Cassiopeia A thing that we've looked at here, is actually a star that exploded in our galaxy in about 1670. And the actual size of it is much smaller than that. It's a tiny spot on the sky. But what we're seeing is a blob far bigger than the size of the full moon. And that's purely because of that resolving power problem. We're using a 7-meter diameter telescope with a long wavelength. We should have been using a telescope far, far bigger than that to be able to see any detail. So the width of that blurry blob that you see, the peak there, is not real. It's just the real thing it should have gone up and down again and across. It should have been a spike on this picture, and it's been blurred out. Okay, so how do we get around that? We get around that by making our telescopes bigger. The problem is you can't really make a telescope much bigger than, say, the Lovell telescope. It's still the 3rd largest fully steerable telescope in the world. So what we do is, instead of making a single large telescope, we get lots of telescopes, individual telescopes. We separate them by large distances, and then we look at the same thing at the same time with them, and we bring the signal back together. So this is our array in the UK. It's called E-Merlin. There's up to 7 telescopes can be connected together. So 2 of them are here, the Lovell telescope and the Mark II telescope, the other big one here. And 5 of them are spread across the country. And they're connected by optical fibres back to here. But they basically work as if they are 7 little bits of the surface of a giant sort of virtual telescope that's the same diameter as the largest distance between the 2 of the telescopes, which is 217 kilometres. So this is a 217 kilometre wide telescope. Okay. So in that equation I showed you earlier, when we worked out in our heads that we needed the human eye was equivalent to a 500-metre telescope, we've now got a 217 kilometre size telescope. That means this gets images that are as sharp as the Hubble Space Telescope gets, and the Hubble Space Telescope only gets those because it flies above the atmosphere and it gets away from all the blurring effects of the atmosphere. So it gets very sharp images. We can match those from the ground in the radio with E-Merlin. We can go even farther than that. This is the European, what's called the European VLBI network. VLBI stands for Very Long Baseline Interferometry. So interferometry is bringing the signals together and interfering them, in other words, combining them so they interfere with each other, constructive and destructive interference. Very long baselines means very large separations between the telescopes. So here's all the telescopes in the VLBI network, European network. You see it's not just Europe, we're very inclusive in radio astronomy. So we go out well beyond Europe, so we've got there's telescopes in Puerto Rico, South Africa, Korea and China, Russia and so on. So at the moment there's up to 22 telescopes in that array. And effectively then you're starting to build a telescope not just 217 kilometres across, but thousands of kilometres across. and then you start to get even far sharper views. And you know, that brings me to this famous picture that was produced recently, which is the first picture of the region zoomed into the region around a supermassive black hole in another galaxy. It's actually in a galaxy called M87. And so it's looking at the radio waves that are being produced around the event horizon of this black hole, and that was done with seven radio telescopes. So not that many radio telescopes, but they were working at a wavelength of 1.3 millimeters. Now, if you can think back to what I was talking about, if I was talking about 21 centimeter wavelength before, and do you remember my equation said the sharpness was lambda over d, wavelength divided by diameter. So if you want better sharpness, you need a smaller number, so you need a shorter wavelength. So going to 1.3 millimeter wavelength from 21 centimeters automatically makes you sharper by a factor of more than 10. And again, you've got these telescopes spread across the whole planet, so you've got that large separation of thousands of kilometers, gets you sharper. But the other, we've been doing this, one of the things that was sort of in a way was perhaps not made that clear in the way this was presented, I don't think, you know, publicly, I suppose, rather than obviously the scientists knew this, but it wasn't perhaps picked up, is that I think people got the impression that it was amazing because they connected together the telescopes across the world. We've connected telescopes together across the world for decades. I've just showed you that European VLBI network, that's been running for decades. What was new about this was the technology they were using to do that connection allowed them to gather a huge amount of information, what's called a very large bandwidth, a very large chunk of the spectrum, very high data rate, 64 billion bits per second from those telescopes, compared to that European VLBI network I mentioned is typically just a few gigabits. This is 64 gigabits, and the more data you collect, the more able you are to produce an image like this. So it's short wavelengths, working at high data rates is what was really it's the technical improvement actually that has allowed them to do this. Okay, I'm going to show you just demonstrate to you how these interferometer arrays work. Just briefly. So if we find this thing here and we run this, it should work. Okay. So this is a simulator written by one of my colleagues here, Adam Avison, and one of his colleagues at Cambridge a few years ago, and it basically shows you what a radio telescope array would see under various conditions, and so you can use different sorts of images to produce this. So you can use this. This is the logo of the European Southern Observatory. But you can do things like, I don't know, you can probably do things like that. Yeah, we'll probably better go back to that. The telescopes are these yellow blobs. So if you had, in this case, 5 telescopes spread out like this, and you tried to take a picture of that, what you would see would be that, which isn't brilliant, right? And the reason basically is that you what you really wanted was a full telescope this size, you know, the whole telescope, but you're actually only got 5 little bits of the telescope. So it's a bit like you know, looking through a pair of binoculars or maybe a telescope, and then getting some black tape and sticking black tape all over the end of your telescope, so there were only 5 little pinprick holes between the black tape left, and then you look through it, you get a very distorted image. Now, of course, you can improve that image by having more telescopes. If I now, instead of having 5, I have 10, Okay, it changed. It still doesn't look much like that logo. What about 30? Okay, so this, now there's various patterns, arrangements in which you can put these telescopes that you can choose in the simulator, and obviously in reality we choose those ourselves on the ground. This is a spiral pattern. You can see that now when you've got 30 of them. And the reason you now start to see an impression of the real thing is because you've actually got what matters is that if you imagine the signal gets built up by combining the signals of all these different telescopes together. So when you've got two telescopes that are very far apart, like the one at the top and the one at the bottom, those are like the large value of D in that equation, that diameter, the long baseline, the large separation. That's what lets you see the fine detail. But any picture like this has fine detail, like the edges of these letters, but it also has big, broad structures like the insides of this star shape. So you not only need the large separations, you also need the small separations as well. So any array of telescopes like this has to have a mix of small separations and large separations, and also it has to have them at different angles, because different angles of pairs of telescopes, a sensitive will see structure that's in different directions on the sky. So obviously if you had loads of money you would have loads of telescopes all the time, but you can't do that. So sometimes you're just stuck with say 5 telescopes. That's what's called a snapshot. So that's just like a very short observation in terms of time. What you can do is you can use the fact that the Earth rotates. So you can actually collect data over the course of a day or something, and as the Earth spins, the object moves around on the sky, and if you imagine you were on the object looking back at the telescopes, you see the telescopes in a different configuration. You see them from the side, and then you see them from above, and then you see them from this side, and so all the sort of separations, the apparent separations, are changing all the time, and the angles between them change all the time. And so if you say, okay, rather than having just a snapshot, I'll allow for Earth rotation in this, then you can start to get better structure with fewer. So if I do snapshot mode looks like that. Earth rotation mode looks like that. Okay, it's not great. Let's try 10 antenna. So this is Earth rotation mode, and you start right. So now, so that's 10 antennas, 10 telescopes, using Earth rotation. Whereas if I'd used snapshot, which I showed you before, then you don't really see much. So the Earth rotation is giving that as extra stuff. So that's what we do with E-Merlin. We've only got 7 telescopes. We have to use Earth rotation to get images from the telescopes. So I don't know, 10 antennae Earth rotation we had, didn't we? And then there's one of my favourite pictures in this thing is this one, and you can sort of see what you get. So it's nice. These things, it's quite a good little simulator to give you some idea. So hopefully that gives you a little bit of an idea of what's involved in, you have to plan how you position your telescopes relative to each other, the separations, the angles, how long you observe for, and so on, to take advantage of this. So we can see what our telescopes are doing live now. So if we have a look at, say, this web page, shows us a live view of what everything our telescopes are doing. So these are all the Jodrell Bank telescopes, both here and across the country. You'll see some of them have been providing. This is the one we just used a minute ago, the 7 metre, providing data to the observing room via that interface I just went to. This 42-foot's observing pulsars at the moment. The Lovell's parked, so it's not switched on. These telescopes are in E-Merlin, as are the 2 at the end, so they're doing an E-Merlin observation for somebody. And then this telescope, which is also part of E-Merlin, is actually having some of its drive system fixed at the moment, so that's why that says control room. So there's a lot going on all the time, basically. There's the control room. That's got the old control desk in it for the Lovell telescope. Big picture windows with a view of the Lovell telescope there. But over in the side of the control room, there's this desk, which is the Merlin control desk for the telescope controller. There's a telescope controller on duty in the control room 24 hours a day, 365 days a year. Tonight is Luke Invernon, but we have 6 controllers who do 8-hour shifts, so 3 different controllers on each day. If you sort of zoom into one of those screens, you can see the sort of control system for Merlin, which has a sort of graphical interface that has, well, in fact, it has our other telescopes as well, the 42-foot and the 7-meter on there as well. But you see the status of the various telescopes, and it sort of also shows you the signal path through Peterborough, from Cambridge through Peterborough to Nottingham, and then they join up forces to Birmingham, to Crewe, to Jodrell Bank, basically, is where the fibres go via a circuitous route. In the control room as well, we have a clock, very accurate clock that uses a combination of GPS satellite clocks and a hydrogen maser clock, which is an atomic clock that we have here to give us a very accurate time signal. We have a very nice traditional chart recorder output for our wind speed and direction. We've always had this chart recorder output ever since the early days of Jodrell, and it's just nice. It shows you the wind direction on the left, I think, and the wind speed on the right, and it sort of shows you the record of it. And you see the pens move. And the big issue with wind with the big telescopes is when you've got them tipped over and the wind blows into them, you could blow the whole thing down. One of the other rooms that you don't often see into is the Lovell observing room. So that has things like this in it, where the signals arrive from the telescopes, mainly for our pulsar observations. So pulsars are the remnants of exploded stars. It's a big area of work here at Jodrell Bank. But after these signals sort of been through this sort of analog bit of kit, they head into here. So it doesn't look massively impressive, but it's basically a whole rack of computing equipment that's all in shielded boxes. So the air can get in and out through these grills, and we have a cooling system that blows air through these computing racks. But the radio waves that the computers are producing don't get out and interfere with our observations. So that's what they look like if you open the doors. There's just lots of racks and racks and racks of computers in the back end, which is how we analyse our data these days. There's a whole, I'm not going to go into detail on all these things, but it's a whole bunch of electronics and computer kit, which various different forms of it are used to do different aspects of our pulsar observing. So these are some of the details of these things, if this is the sort of thing you're interested in. Lots and lots of different computers sitting in this rack, all taking different bits of the radio spectrum and processing it in real time. And it also includes stuff from other telescopes around Europe. Some of the data is just copied directly onto these discs in here. Sometimes they'll send us discs, post us discs, and we put them in there, and then we analyse them with all the computing stuff on the right-hand side of the modern things that we're doing. And we're constantly these things change all the time as technology improves. So, for example, this little box in here is basically a computer on its side. In there, it's called Hebe2 for reasons I don't know. But basically, that is a GPU-based computer. So, some of the fastest ways to calculate things these days in the era of in the region of computing is things called GPUs, graphical processing units. So they were developed because of the huge amount of money involved in computer games. So because people who do all these if you're into computer gaming, you're doing all these real-time calculations and real-time graphics, that requires a huge amount of computing power. There's so much money involved in computing globally that the technology companies develop these GPU systems. We then just buy them in and use them to do radio astronomy. So actually that's the way things have moved. in recent times. So a lot, again, this is another GPU-based system. It's actually these three computers over here in the dark are this transient system that looks for signals like fast radio bursts and so on from the flashes of radio waves from distant space. So we do that in real time from 6 of our telescopes. If you're keen on computers, we do have a VAX. I don't know if anybody's of that era. And we're still using it. It's called Arthur, since we had a telescope called Merlin. And it's basically because that's involved in the telescope control, so the driving the telescope stuff. And it just works. And the only reason we will move away from it, we've got a computer sitting in that rack waiting to take over from it, is because it gets harder and harder to fix these things, to replace the components as they break. So eventually you do have to move away from them, I'm afraid. But you know, if we have a quick look at some recent pulsar observations, we should be able to see. Let's have a look. There we go. So these are some of the most recent pulsar observations. They date from earlier today, so around lunchtime. And if I just sort of scroll back through them to find, that's a very faint pulsar. There's a brighter one, a couple of brighter ones. So you basically see if we can get an even brighter one. There we go. So basically what you see is the flash of radio waves from the pulsar, these rotating lighthouse beam type things. So they've got a rotating beam and you get a flash every time they spin. This is the sort of spin period, which for this pulsar is says at the top, 0.358742 seconds. So every 0.358742 seconds, and we will know that number to even more decimal places, it flashes. And you see the flash here and in various other ways there. So we time these things all the time with the Lovell telescope when it's available. These would have been done with the Mark II telescope because the Lovell's unavailable at the moment. And we also use the 42-foot telescope as well for some of the brighter ones like the Crab pulsar, for example. So we've got more than 800 pulsars in our catalogue. And we have observed them for up to 50 years in some cases. They were discovered in 1968, so we've got this continuous record of timing these flashes. And with that, we can do loads of interesting things to do with, not only understanding pulsars themselves, but studying the stuff between the stars, the interstellar medium, studying general relativity in the way these things orbit one another, and so on. A great database. Across the corridor from the Lovell observing room is the VLBI observing room. This is a picture of the racks in the VLBI observing room. It has a bunch of stuff in here. Over on the left-hand side here is some recent stuff we've got from a project called Breakthrough Listen, which is doing the search for extraterrestrial intelligence, and we'll have more to say about that in the future. In the middle we've got the VLBI systems, so these things where we link up with the telescopes across Europe and beyond. There's a whole bunch of disks here where we basically now record all our data onto these hard disks, and then the central system in the Netherlands copies the data across a dedicated fibre connection dedicated light path connection to the Netherlands. Historically, we used to record on magnetic tapes, and then we used to have to post the magnetic tapes to Holland, and then they would read them off again. Then we moved to hard disks, and we used to post the hard disks to Holland. And just very recently, we've moved to just copying it across the internet, basically, because the bandwidths are going up and up and up, so it's changing what we can do. On the right-hand side, the yellow cables are the ends of about 600 kilometres of optical fibre that's buried underground across the UK that links our e-Merlin system together. Yeah, sorry, I should show you that really. This is actually how VLBI works. 3 sessions a year lasting 3 weeks each, where we link together these telescopes across Europe. And then occasionally, sort of once a month, for a day, for 24 hours, we do live, rather than recording it onto the discs that I just showed you and then copying it across over the course of the next several weeks. We do it all in real time to Holland from here, from all of our telescopes, and we link things up real time. That's the band, the radio spectrum visible in the VLBI room there. I should just say something about radio interference. It's very bad in some parts of the spectrum. Something like 30 to 40% of the low frequency part of our spectrum gets thrown away because of interference, and it's better at the higher frequencies. It's what's called C-band. But if you're interested, just to show you what it looks like, the raw spectrum, it's a bit like the waterfall plot I showed you earlier, that if you remember, from the 7 meter. That top strip is the original data, and the strip underneath, all the white bits have basically been deleted. So they were what we would call interference. Some of it is, well, most of it's people using mobile phones and things. So people using the mobile phones and whatever wouldn't think of it as interference, but we do. And so we patch all this stuff out as automatically as we can. But in fact, to do the best job, you have to do some of this manually, and we end up with, you know, as you say, we can lose a significant bit of data. So we're always interested in trying to remove interference. In the corner of the room, there's a shielded room, that blue door. Inside that blue door is our supercomputer that combines the signals from the Merlin telescopes. It does 10 to the power 15 calculations per second. So that's 1,000 million calculations every second. And it combines the signal to an accuracy of a millionth of a second when we bring the signals back together. So it's a very special purpose computer. And we make things like images of, this is a recent Merlin and VLBI image of a colliding galaxy. So two galaxies 250 million light years away began colliding about 700 million years ago, and they're merging together. And in that collision that you can see on the left-hand side in a Hubble Space Telescope picture, when you zoom into the middle, you see the sort of nuclei of the two galaxies coming together. That causes a burst of star formation. We think it's called a starburst galaxy inside that region. And so when you form a lot of stars also die. They explode in supernovae. So in this picture on the right-hand side, the big coloured, this is a zoom in very right into the heart of here. This is our radio image. The two blobs are the two nuclei seen with E. Merlin, and then at even higher resolution, even sharper view, you see the little black dots. They're all stars that are exploded that we see with the planet-sized radio telescope with the VLBI. So that's now standard practices to observe these things, to combine all these telescopes together. Oh, just a picture on the wall of the VLBI room. A little visitor we had who was fiddling about with our settings in the VLBI room. Right, and the last thing I'll show you, just a very recent observation we did. If anybody's interested in music, there's a famous Manchester band called Joy Division who morphed into New Order, who are playing at Blue Dot Festival in a few weeks' time. But it was 40 years ago last week since the release of Joy Division's sort of famous album called Unknown Pleasures. And on the front cover of Unknown Pleasures is this picture, which they just lifted from a Cambridge Encyclopedia of Astronomy. And it's an Arecibo telescope observation of the first pulsar discovered by Jocelyn Bell in 1960. Well, she discovered it in 1967, published in 1968. So we did an observation of this thing ourselves last week, just to commemorate that, and that's our version of the same thing with real data. I'll see if I can play the sound. I didn't try this earlier. Oh, no, I can't. You might be able to hear it. That's the flash of this rotating object. It rotates every 1.3 seconds. So that was just a bit of fun, really. And my last slide, basically, I mean, I hope I've given you some sort of, I mean, it's a bit different to a normal talk where we not talk much about the science, but it's sort of a bit of the behind the scenes. And I think one of the things I would take away from it, and hopefully you might, is the most obvious part of this observatory are the telescopes. You come here and you see the big Lovell telescope, or you see one of the other ones across the field. They're basically just big lumps of metal shaped like a paraboloid. So they collect radio waves and they focus them all to the top of the tower where the receiver is. The big lump of metal, you can basically, as long as you maintain it, you can pretty much leave that the same if you like. Okay, we've had 3 different surfaces on the Lovell. We've made them smoother and therefore improved that. But the key thing is that the receivers that pick up the radio waves can be improved and have been over the decades. The chunk of spectrum that you pick up at any one time can be increased because your processing power, your technology improves, and all that back-end computing is continually changing as the technology develops. So the bottom line is we do keep getting better, even though actually when you go and you might look at the telescope and think, well, it just looks the same as it did 40 years ago. All the back-end stuff is remarkably different and far more powerful than it once was. Right, I think that's me finished. Thank you very much. Sorry, we can probably do a few questions. I don't know, should we put the lights on and see whether we can, and I'll so we can see people. Is everybody awake? Oh, yeah. Painted open eyes on your eyelids at least. Does anybody have any questions you want to ask? Or okay, there's perhaps one down the front here. So have we got more than one microphone? Or because I'll share this one. Yeah.
Okay. So you have access to one of the greatest telescopes in the world, I guess.
Yeah.
A lot of professional astronomers say, I have access to such great telescopes, I don't own my own optical equipment. Do you have an interest in that?
Oh, I don't need your microphone.
Oh, right,
I've
okay.
got my own microphone. Well, funnily enough, I never used a telescope. I never looked through any type of telescope until after I got a PhD in astronomy.
Yeah.
I'd not even looked through any small telescope, which is a bit strange, but not that strange for what you might call a professional astronomer. So yeah, I did my PhD on a star that exploded in 1985, and I've never looked at it. I didn't even know where it was in the sky after I'd finished my PhD. It never crossed my mind to go outside and go, oh, that star I'm studying is up there, which is a bit weird thinking back on it. Since then, I've got better. I've improved. So I've used telescopes all the way across the spectrum, and I do have my own. I've got several of my own telescopes actually. So yeah.
We were at a talk once where 4 professionals all sat there and said, "No, I don't own anything." So
some professional astronomers take pride in not knowing where everything is.
Yeah.
I think it's a little bit weird. You'd probably be better off knowing where things are.
One was too poor to it, his early years, early career. But
yeah. Is there somebody else? I'll give this person here first, and then.
Thank you. You said technology is getting better. Where do you see Jodrell Bank in the next, say, 10, 20 years? What's the future look like?
Yeah, I think it's hard to see. I think it's hard to see even as far as 10 to 20 years, to be honest. I mean, when the Lovell telescope was built, Bernard Lovell thought that it would last about 10 to 15 years. But actually, it's still operated and is far more powerful than it was back then. So it's a bit hard to predict the future. We've got a number of upgrade paths for our telescopes here. So there's things like, looking into the nearer future, we've just took delivery of a thing called a PAF, a phased array feed, which is like a multi-pixel camera that will sit at the focus of the telescope, that will improve our survey speeds and so on. We've also got plans to we'd like to include a telescope at Goonhilly in Cornwall as part of the emailing array, for example, which would add power to that. But we're also working on, not just on the telescopes here, we're working on things like the square kilometre array, for which the headquarters is just next door to us here. But we've been involved in designing that telescope for years, and we will use it to do lots of different observations. It's just it'll be a much bigger telescope, so an area that's 220 times the size of the Lovell telescope, so we'll be able to see much fainter things. Yeah. Was there someone? Yeah.
So you said the emailing had 3 weeks a year. when it functions?
VLBI actually, yeah.
Oh,
Sorry, I did shoot past that slide.
How do you choose which 3 weeks? Because it's not a very big time lapse.
Yeah, so that was the VLBI system with all the European telescopes, and that does 3 sessions of 3 weeks a year. So it's 3 lots of 3 weeks. And the reason it does that is because all those telescopes are owned by various institutes in those various countries, and they've got their own things to do the rest of the time. So we sort of join forces to say, okay, we'll all work together on this project for these sessions, and they're planned well in advance, so we know exactly what the dates are for years in advance. But it's only because of, you know, outside of those sessions they're doing their own observations. So our emailing telescopes will be doing emailing stuff like they're doing it now, but a few weeks ago we were doing VLBI, we were doing these European telescope observations with them. So that's the way it's just a scheduling process, and we try and use them all 24 hours a day if we can, all year round. Sorry, you can hold it.
Yeah, no, that's all right. So you're mentioning the square kilometre array. Do you process much of the Meerkat data back here? Because that's kind of part of that, isn't it?
Yeah, so Meerkat is a precursor of the square kilometre array. Meerkat is a 64 telescope array in South Africa. So the South Africans have built that, and that's operating now and is doing incredibly well. We again have been involved. We're involved in a number of projects that use Meerkat data. So particularly the Pulsar group here use Meerkat data. So some of the computers in that room have been processing Meerkat data, for example. But basically it's run by the South Africans, and we are collaborating with them to work on stuff. But yeah, Meerkat produced a beautiful picture of the centre of the Milky Way last year when it was inaugurated. So it's going to be a spectacular 64. Remember my little simulator, and I was showing like 5 telescopes, 10 telescopes, 30 telescopes. 64 telescopes is a lot of telescopes, so you can produce a really high quality image in a short amount of time when you've got that many antennas. So yeah, that's what makes it great. Any other questions? There's yeah. Should we? We'll split. Oh, you're going to the back. Pass that. We'll go. Was there someone here as well? We'll go this way first. You pass that along. We'll do the back first.
You collected, or you've talked about terabytes of information. You get the impression the whole of this area of science is collecting vast amounts of data. Is there a real issue emerging of analysing the data we're collecting now?
Yeah. Yeah, sure. You have to. I mean, we collect far more data than when you process the data, you often are able to throw away a lot of it, and you use the data products in that sense. In which case, the data's. But sometimes you end up with so much data in these things, it's hard to see it because you can't even get it on the computer screen to look at it. You've got to zoom and zoom and zoom and zoom, and then you've lost a sense of the big picture. So actually, developing ways in which we understand and analyse the data is a key part. We have to work out better ways of doing that. So I think it's, I don't have a great answer to that other than you're right. There is a huge amount of data and it's very hard to process. Artificial intelligence might have a role. Certainly, we've got people working on neural network systems that can perhaps automatically. I mean, even that interference example I showed you is done automatically through those sorts of systems, for example. But other things where you're searching for a particular type of signal, you can, if you're clever, you can produce a program that might find you those automatically. It's quite difficult and a bit dangerous because it'll find what you tell it to find, and then it won't find the things you don't tell it to, and you might miss stuff. But yeah, we can only do what we can, I think. Was there ones?
Yeah. You said earlier on we've been looking at some pulsars. You've been observing some pulsars for up to 50 years.
Yes. What's
changed in 50 years, or is that too short a time in astronomical terms?
What's changed?
Yeah, what have you observed from the first to the last observation?
So pulsars generally slow down. So they're slowing down because they're radiating away energy.
So that's measurable in 50 years?
Oh yeah, it's measurable in days and or weeks, that sort of time scale. You can see you can measure a slowdown rate. So very recently, one of our students found the biggest ever what's called a glitch in the Crab pulsar. So there's a pulsar in the middle of the Crab nebula, and our 42-foot telescope has been following that for decades. And what happens is they gradually slow down because they're radiating away energy, and every now and again they speed up suddenly and then start slowing down again. It's called a glitch, and it's a bit random. And we think it's something to do with the structure of the neutron star itself. So we think there's probably a neutron star crust with a sort of superfluid interior, and as it slows, these things get out of step and then maybe catch on to each other again. So maybe the interior is spinning faster than the exterior, and it then catches on, spins it up again. If you see, but there's loads of stuff you can see in these things.
Very changeable. Then.
Yeah.
Thanks.
And so, I mean, one of the other things is we've got a project that LEAP. I've flashed past some of the slides, but you can go watch the live stream afterwards, the YouTube, and pause on my slides. But there's a thing called LEAP, which involves connecting together telescopes all the way across Europe to look at pulsars, and we're looking at very fast spinning pulsars, and we're looking for variations in the pulse arrival time when you look around the sky, and we expect to see variations because of very long wavelength gravitational waves, sort of ripples in space-time that are flowing through us all the time, caused by the collisions of supermassive black holes. So we found these gravitational waves from the collisions of lower mass black holes, weighing maybe 20 times as much as the sun. Well, these big ones at the middles of galaxies are billions of times the mass of the sun. When they collide, they produce these very long wavelength gravitational waves, and pulsars are one of the best ways we can do it.
Yeah.
So looking at the timing signal over decades from a set of these pulsars is what we think will help us discover those. So yeah, but that's just a few examples. There's more than that. Oh, sorry. Well, wait a minute. We'll pass that there. Yeah, go on.
What's the best thing you've seen?
What's the best thing I've seen in astronomy? I was going to say. I think it might be Ole Gunnar Solskjaer's second goal, and I was standing behind the net in the new camp when those goals went in. That was one of the greatest experiences of astronomy. Best thing I've seen. Well, so I suppose it's not with my own. That star that I did my PhD on. So everyone loves what they did for their PhD. It's like harking back to the good old days or something. And that star that exploded in 1985. It has sort of repeated explosions, and it exploded again in 2006. And so we then had much better technology, much better telescopes to look at it than we had in 1985. And we got we got a planet-sized telescope array to look at it. And there was a bunch of us sat in the room down here in the dark on a Friday night, and processing the data and all sitting around the computer screen. And then what appeared on the computer screen was this sort of circular thing, looks a bit like that black hole image, this sort of circular thing, a bit brighter on one side. And that was basically the shock wave that resulted from the explosion, as that shock wave sort of travelled out through the wind of a red giant star in this binary star system. And you could see it, and you could measure its size, and therefore you could calculate its velocity, and you could work out the temperature of the gas, and it all fitted this sort of model that we produced for the X-rays that come from it. So that was quite exciting, because we had a picture in our head of what would happen, and then we took a picture of what was actually in the sky, and we could it seemed to agree with what we thought was what we'd imagined, I suppose. Yeah, go on. So,
on the email, basically, it's set up. I've got quite a number of telescopes, which seems to be quite far away from each other. So that increases the area. What's the advantage of having them closer to each other? I mean, you've got two in here, for example.
Yeah.
What would you get from that?
Yeah. So the question was, so when in an array, when you've got telescopes far apart, I was talking about seeing fine detail. What's the advantage of having telescopes closer together? If you only had telescopes that are far apart, then you only see fine detail. You don't see broad structures on the sky. So, I mean, I don't think we've got time really, and it's a bit warm, so I won't go back to the simulator and show you, but you could use the simulator to demonstrate. If you had something, where you had, well, in fact, that picture that I showed you with, that one there, these big broad structures are seen with the E. Merlin telescopes, which are within 100 kilometres of each other, whereas the little tiny spots are seen with the telescopes that are thousands of kilometres apart. The telescopes that are thousands of kilometres apart can't see these big things at all. They don't see them at all. So these black dots would be all they'd see. So yeah, so the bigger things you see with telescopes closer together, it's almost the opposite. You know, the bigger things on the sky you see with telescopes closer together. The finer, tiny things on the sky you see with telescopes that are farther apart. And you basically need to combine the two to get a proper picture. Are we more or less, oh goodness, sorry, I nearly said, oh goodness, oh goodness. Go on then, shout them out. 2 last questions. Is funding a problem? Yes, always. But that's as it should be. You know, we shouldn't expect to be given money for, you know, for nothing, you know. Are there international agreements on how research should be funded? None, well, international agreements. Well, the closest you get, there are national agreements, right? So our government, most of our funding comes from the UK government. Some of our funding comes from the European Union. So the European Union has a big funding agreement. So that's an international funding agreement. And we get a significant sum of money, particularly for people, actually, from that project. So we are big fans of the European Union at Jodrell Bank. So we're not great fans of Brexit, I'm afraid, for lots of reasons. But that, you know, that's sort of maybe a parochial one. But we are funded by them. But that's international. It varies a lot. There's a lot of private telescope projects might even be funded by rich individuals sometimes. Who fund the telescope, and then, you know, they give it to a university, say, and that university builds and operates a telescope, and to get to use that telescope you have to work with them and contribute your time and your resources and your ideas, and then you get to use the telescope. So there's lots of different models for how we work together, but it's very collaborative. Yes?
Just going back to your pulsars, when you have a flash come past the Earth, how wide is the beam?
Oh, how wide is the beam? That's a good question, isn't it? I should be able to work that out. What you'd have to do is you'd have to sort of you can sort of work it out from those pictures I was showing you earlier. I'm not a pulsar astronomer. If I was a pulsar astronomer, I would have been able to tell you that straight away, I'm sure. But if you looked at pictures like I don't know, like that one there, then you can sort of see the width of the flash, if you like. It sort of tells you the width of the flash in time units. This is time along here. So that width there is the rotation period. The rotation period is 0.23 seconds. So this is about 0.05 of 0.23. So it's 0.023, 0.01 seconds. So it's swept past you in a hundredth of a second. So I suppose it's a fraction. Suppose this is a fraction. If that's 0.05 of the width, then the full width is 360 degrees around, isn't it? So it's 0.05 of 360 degrees wide. So that's a tenth would be 36. So 0.05 would be 18 degrees. Sounds about right. I'll stand corrected by an actual real pulsar astronomer. But yeah, you'll be broadened a little bit in here by the bandwidth of the observation as well might affect it a little bit. But that'll be about right. 10 degrees to 20 degrees probably is the width of the lighthouse beam. That's what we're talking about. Right, I think it is a bit warm, isn't it? I think we should probably finish. Thank you very much for coming, and I hope to see you again here very soon. Thank you. I have to work an hour.